It's a pleasure to welcome Jaikumar Radhakrishnan to the Communication Control and Signal Processing Seminar Series. Jaikumar holds the position of Senior Professor in the School of Technology and Computer Science at the Tata Institute of Fundamental Research in Mumbai. And Jaikumar is appearing from there now. It's 8:30 p.m. or 8:33 p.m. In India now. Uh, Many of us who are in information theory were introduced to Jayakumar's work through his classic paper, Entropy and Counting, and the beautiful entropy proof of Shearer's lemma. Jayakumar, of course, has made numerous leading contributions and influential contributions to approximation algorithms, communication complexity, quantum computing, and circuit complexity, by way of algebraic methods, combinatorics, information theory, and probability. So to me, in the parlance of jazz, Jaikumar is a superb exponent of the fusion of ideas from these fields. So Jaikumar, it's a pleasure to have you here. We look forward to your talk. And as Sasha mentioned, for the viewers and the listeners, your talk is posted at the seminar website. There's a link also in the chat box, and you can follow his lecture also through his notes. So Jaikumar, all yours. Thank you very much and welcome.
Before we move, Jaikumar, the camera is not quite picking the focus of the board. Can you shake it somehow so that it behaves better?
Yeah, so I think maybe different parts of the board are focused differently.
Okay.
I think if I move closer to the board, it sort of picks it up. So yeah, I don't know what to do better than this at the moment. So,
that's okay.
So, all right. Thank you very much for the introduction. Thank you for the invitation, and thank you all of you for coming. So I believe I have about an hour and 20 minutes. Is that I can't hear.
It's 90 minutes, 90, and it's also flexible. Yeah.
All right. Okay. So yeah. So the talk is about zero error list decoding. So let me tell you what the q-1 channel is. So it's a channel which has, yeah.
I think if you shift the camera a little farther away, you won't lose in size, but maybe it will focus better. It just shifted a little bit farther away from the board.
Okay, let me try.
Yeah. So sorry much better. It's improving. Yeah.
Okay, so I didn't do anything, so it's
it's just the thought of it. Now, if you push it, it'll be even better.
This is very good. This is much better. Thank you.
Beautiful. Thank you. Yeah, perfect.
This?
Perfect. Thank you.
Okay, good. Yeah, I didn't do anything. Yeah. So anyway, so the q-1 channel has an input alphabet sigma, which has q symbols x1, x2, xq, and the output also is the same alphabet. So this is what the q-1 channel is. But here's what it does. If we write it like this, x1, x2, xq, x1, x2, xq. And when x1 is sent in, what comes out could be anything other than x1. So the probability, if you want to think about it in terms of probability, then the probability of getting x2, x3, or xq on the output when x1 is sent in is non-zero, is positive. And the probability that x1 itself arrives at the output is 0. Okay. So if you feed in x2, everything other than x2 itself is possible, and similarly for xq. So yeah. Now, if you use such a channel, what can you do? Yeah. So we have a code which has block length n, and the code is this C. Now, unique decoding is not possible for this channel, because if you give me any q-1 code words, yeah, so this is one code word W1, W2, W2-1. Take any q-1 code words, there is a word which is compatible with all of them. Okay. Because if you look at the first symbol, there are at most q-1 different symbols here. And there is always a particular symbol which is connected to all of them. Okay. So that you can build up some received word, let's say y1. Similarly, when you work on the second coordinate, you can build a second character of the received word, and similarly for the last one. So if you give me any q-1 code words, there is a received word which is compatible with it, which means if you receive this as your received word, you would not know which one of these is possible. So as a result, if you want to do unique decoding, it's not possible with this channel. So now the question is, how well can you do this decoding? That means on receiving a word, the receiver has to produce a small list of words and guarantee that the word that was sent in was one of those code words. Yeah. Now, this example tells you that, yeah, so let me just write down the definition. C is an N. So we say that a code is N list decodable if you give me a received word, there are at most L code words that are compatible with it. Now, and we say that the capacity of is, let's call it, yes, let me just write supremum as n goes to infinity of log of the size of the code divided.
2 lines above, did you mean to say L code words?
Oh, sorry. Thank you. Yeah. At most L code words compatible with it. And now we define the capacity of this channel, that is the QL capacity of this, or the L, the list of L, size L capacity of this channel to be the maximum number of code words you can pack into a code while ensuring this property, that is every received word is compatible with at most L code words. Now, what this example tells you is that if you insist on a very small list of size, say q-1 or smaller, then your capacity is 0. Yeah, you can never. Yeah. But so we can ask. I'm sorry. If you want lists of size q minus 2 or smaller, then this capacity is 0. So the question is, how does this capacity behave as we increase this L? So the first interesting value is L equals q minus 1. And yeah, so capacity Qn is 0 if L is strictly less than q minus 1. And it turns out that for L equals q minus 1, it's possible to construct codes which have positive capacity. But these capacities are very small. So let me write down. What we know about the q minus 1 capacity. Both these numbers are exponentially small. And we have at some level pretty good upper and lower bounds, except here you have a square root k and k to the 1.5. And assuming that, sorry, I keep writing k when I should be writing q. There's a place in the notes too where I've made this mistake. So the capacity, if q is large, is very small, exponentially small in q, and the upper and lower bounds are off by a factor q squared. So this is called the Friedman convolution. And we will see how such a thing is proved. Now, this is for large q. And the problem is interesting for small q as well. So perhaps the most famous problem in this line is the capacity 3,2, the case when q is 3. Okay. And so the precise bounds here are not known. And this is the famous difference problem of Turner's, where he would, so the question is, what is the truth? That we have a gap between the upper and lower. So let me just state this problem in a different way. So our alphabet, Q is 3, and we're trying to build a code. So let me write down the code words as rows of a matrix. So this is our code, and we have fixed an M, and we are asking how many code words can we produce, so that if you pick any 3 of them, there is some coordinate where they all differ. So if you pick any 3 code words, there should be a coordinate where they all differ. And understanding this number is the same thing as understanding the maximum number of words you can obtain, so that this property works. Okay. So that's why it's called difference. The same question when instead of 3, you have an alphabet of size 2. That's more or less trivial. How many strings can you produce so that every 2 strings differ somewhere? Okay. So the notion of difference has been generalized to alphabet 3, and it's called difference here. And this is the state of the art right now, as far as I know. problem is also interesting. I mean, there has been some recent work on the next interesting channel. So here,
Jaikumar,
question.
Prakash, not that it's needed to. What was the provenance of this channel model originally?
Sorry,
what was the source of this channel model? How did this model come about?
Yeah, so I myself don't know, but this was a channel studied by LIS.
Okay.
Yeah. Now, the paper is from the late 1980s, but I understand that this was something he had studied much earlier, maybe 20 years now.
Okay, thanks. Yeah, thank you.
So the capacity of the 4-3 channel was already considered by LIS. And there is another way of viewing the problem of capacity q-1, which I will refer to later, where it corresponds to families of perfect hash functions. Okay. So although in information theory we call it the zero error list decoding capacity problem, it has another incarnation as families of perfect functions, perfect hash functions. The point is that we should think of each of these columns as a hash function which assigns a symbol in the range 1 to q to each of these rows. And if you pick any q rows here, one hash function maps them injectively. That is, it assigns different symbols to each of those 4 rows. So yeah, we'll talk about it very soon. So for the 4-3 channel, what is known right now is, let me make some space here. This number is 0. So things are pretty bad for such small numbers. Okay, so in general, for large Q, we seem to have the right exponential in place, but there are these polynomial factors which are off. But for small values, the numbers that arise out of bounds like this or some improvements of these look pretty bad. So what I'm going to do today is, I assume that not everybody has seen the Friedman-Komlosche bound. So I try and describe how this comes up. And all of these bounds that I'm going to talk about today, they have this combination of, there's a notion of density, which gives you this exponential part of the bound. And there is an entropy consideration, which gives you another factor. And it is the combination of these two which give rise to these upper bounds. Lower bounds, most of the time, are just random constructions. However, this lower bound requires some other more ingenuity than just plain old random construction. So, all right. So I'll just write down one last question. So I'm going to tell you about this. I'm going to tell you about this one. And one more thing. So one could ask, all right, we're just at the brink. So for q = 4, list of 2 is not possible. Capacity is 0. The first time you can have something non-trivial is 3. And then we are trying to ask, what are the bounds? Here, q-2 gives you 0 capacity, and q-1 things are exponentially small. So we can ask, how big should the list be so that we start getting decent capacity? Now, what does decent capacity mean? So let us say for today, decent capacity means inverse polynomial. capacity like 1 over q or 1 over q squared, it should not be exponentially small. So the question is, so for what value of L can we hope to get a capacity which doesn't grow, doesn't fall exponentially, but we are able to keep it at least 1 over polynomial for some polynomial in Q. Now, a probabilistic construction tells you that I'm not emphasizing the constants here. So you need to go to list sizes of q log q to get inverse polynomial. That this is what we know how to construct. And the question was, is there an upper bound? Can we show that if you keep your list, say, constant times q, 10 times q, then you cannot get such rates, such capacity. And so with a student here, Siddharth Bhandari, what we'll be able to show is that if your list is much smaller than q log q, then the capacity does fall. So think of epsilon as a very small number, let's say 1/10 or something. Then if you insist that your code be epsilon q log q list decodable, then your capacity will be inverse exponential. So if your epsilon is 1/10, then it is exponentially minus q to the half. So these proofs, all of them roughly have the same flavor, but the underlying combinatorics starts getting complicated as we go from here to here to here. And so I will try and describe these three things. That's the plan. So if there are any questions, please ask whenever. So in the abstract I circulated, I also mentioned that we will touch upon graph entropy along the way. So what I'm going to do is I'm going to erase everything now, and I'm going to just talk about a particular graph covering problem. And from that, we will somehow get to graph entropy. And then I will come back to these problems. I will write down these bounds again and we will verify them. So basically, I'm starting all over again. So here's a problem, which is you have G1, G2, Gt, which are bipartite graphs. And the union is the complete graph. And these are bipartite graphs on vertex tech. Let me call it M here. So you have these bipartite graphs. and that union is the complete graph on n vertices. The question is, how big must P be? And this is probably the fundamental theorem of information theory, which tells you that T has to be at least log n, because to say that the union of these bipartite graphs is this complete graph amounts to encoding every number, every vertex of the, every vertex in the range 1 to n by a binary sequence of length p. Because you call one of these parts 0 and the other part 1. With every vertex, you assign either a 0 or a 1. And if it is isolated, you can assign it 0 or either 0 or 1. And then we know that if you pick two vertices in this complete graph, there must be a place where one of them gets a 0 and the other gets a 1. Okay? Because that edge between those two vertices is present in one of these bipartite graphs. So what we have managed to do is to assign each vertex here a sequence of length p over the alphabet 0, 1, such that every two such sequences differ in at least one place. Okay. And we know that to encode n things using binary sequences, you need at least log m many bits. Or if you want to say it in graph theory language, each of these graphs, their chromatic number, they are two colorable. They can be colored in two colors, whereas the complete graph needs m colors. And when you take unions of graphs, the chromatic number goes only as the product. So 2 to the power t must be at least m. So p must be at least 1. Now there is a variant of this problem, which I'm going to call Anson's lemma. Now this lemma was proved in the context of circuit complexity, and it has been rediscovered by many people. I'm sure, like at least, more than 75% of the audience knows this, except that they don't know the name Hansen associated with it. So let me just say what the lemma says. So let n of gi be the number of non-isolated vertices G. So this bipartite graph, how many non-isolated vertices does it have? That is n of g1. This is n of g2, n of g3, n of g2. So the point is that if you're told that you're trying to build the complete graph on n vertices using bipartite graphs, but further told that these bipartite graphs are small, then is the statement clear? If all bipartite graphs were full bipartite graphs, they involved all the vertices, then each of these would have been 1, and this summation would have been greater than or equal to log n. So the fact that this quantity is at most 1 implies this. So this is a generalization of this statement. Now what we will do is we will try and prove this in two different ways. Okay. We'll try and prove this in two different ways. One will be a combinatorial argument, and the other will be a sort of information theoretic argument where entropy will show up. And it will turn out that these two arguments, when generalized, lead to two definitions of graph entropy, and we'll discuss that.
Quick question. So what is in the denominator here?
Sorry.
Okay.
Should have been n. Yeah. So these are all graphs on n vertices, and only n of gi of them are non-isolated. The rest are isolated. The fraction that is non-isolated is this number. Yeah. Want it to be n.
Okay.
Is that okay?
Yeah.
So yeah, let me try and describe the two proofs. So you have these graphs G1, G2, G2, and the union is the complete on M vertices. So here is a probabilistic argument. So one proof will be probabilistic, the other will be so-called information theoretic. In the beginning, they will look the same, but somehow they lead to two different definitions of graphing. So in each graph, so delete so you go to the first graph and you toss a coin, and either you delete this part or you delete this part. Yeah. Now you're left with the rest of the graph, these vertices. Go to the next graph and delete one of the two parts of this graph from this. The isolated vertices don't do anything. And then you go to this part. And in the end, what's the probability that a vertex V survives? So what's the probability that a vertex V survives? Well, if the vertex V appeared k times in the non-isolated part in this entire picture, then its probability is 1/2 to the k. It has to survive k attempts to kill it. Yeah. So where k of v, k of v is the number of graphs in which v appears non-isolated. Is that okay? Yeah. So what is the expected number of vertices that survive? Is so you have these m vertices. Each of those vertices has probability summing 1/2 to the k of v of survival. Yeah. And so this is the expected number of vertices that survive. And what do we know? Because every pair of vertices is separated in one of these graphs. In the end, no matter how this random process evolves, there will be at most one vertex that survives. The vertex V and vertex W cannot both have survived because there is a graph in which V and W appear on opposite sides, and one of them would definitely have been deleted. So this number is at most 1. So now, so we have this inequality. Now, let us just take the average. So I'm going to just apply the arithmetic mean, geometric mean inequality here. So what should I write? N times the product over all vertices of 1/2 to the k of v to the power 1/n is less than or equal to 1. And this I'm taking logs now. But so there is the M which we wanted. Here we are summing up the number of non-isolated vertices of all the graphs. And here we are summing up the number of times each vertex appears non-isolated. Okay. So this sum and this sum are the same, and this implies, yeah. This is what we wanted. Is this okay? Yeah. So what did we do? We just deleted one part of each bipartite graph, did this little computation, and concluded using the arithmetic mean geometric mean inequality that the total number of non-isolated vertices in all the graphs put together is at least m log n. M log n. So let me just leave this calculation here, yeah, and just tell you another way of saying the same thing. So I'll again set up a probabilistic experiment, that is, pick so I start with a complete graph and pick one of its vertices at random. Okay. So I pick one of these vertices at random, and let me define some random variables. Y1, Y2, Yn. This is, yeah, where Yi is 0 or 1. 0 if B belongs to AI, 1 if B belongs to BI. What do I mean by that? This particular graph GI has this set of vertices, which is AI, and this other set of vertices, which is BI, and then there are these isolated vertices who don't have a name. Yeah. So the random variable Yi is 0 if B belongs to AI, 1 if B belongs to BI, and is 0 or 1 with probability half otherwise. All right.
You have T YIs.
Sorry?
YIs goes from Y1 up to YT, not YM.
Thank you. So for each graph, we have one variable Y1 to Y2. Thank you. Yeah. Now, once you tell me Y1 to YT, by the same reasoning that we had before, the value of V is completely determined. Yeah. So the mutual information between the vertex V and Y1 to YT and let me check this. So I'm just using this inequality here. And if you ask, what is the mutual information between Yi and, actually I should not have done this. Okay. Anyway, you set up these random variables in this fashion, and you turns out that if you compute the mutual information between the vertex V and the random variable yi, which is a 0, 1 random variable, then this quantity is at most, it's exactly n of gi over n. And you recover Hansen's lemma. Okay. So yeah, so we will be using Hansen's lemma later on when we describe when we discuss the Friedman-Komros bound. But right now, what we have seen are two proofs of the lemma. One goes by something like this, and the other one was somehow using a random experiment and then the arithmetic mean geometric mean inequality. Okay. Now, what I want to do is I want to generalize this. So this doesn't have any connection to our discussion about the channels. Okay. So what I want to do now is just tell you about graph entropy in general and how these two methods of proof give rise to two definitions of graph entropy. It turns out later on that those two definitions are actually the same definition, meaning the quantities that they define are the same, but that needs a separate proof, which I will not do. Good. So yeah. So how do we go from here to graph entropy, and what is graph entropy? So suppose we had a very similar problem. That is, we have been given some graphs, and the union is the complete. And let me first talk about the first proof. Yeah. So what is the situation? The union is the complete graph, and each of these is not necessarily bipartite. It is some graph. And what should we do if we wanted to imitate the same random experiment? So what we would like to do is, in each of these graphs, we pick one independent set and delete everything else. You remember, when we had a bipartite graph, we deleted one part. Okay. Instead of thinking about it like that, yeah, instead of thinking about it like deleting one part, what we say is we retain an independent set in the graph. Okay. So in each of those graphs, as we went along, we picked one of the independent sets at random according to some probability. We don't bother too much about it. And then we retained that independent set, deleted everything. Then we went to the second graph, retained one of the independent sets of that graph, deleted everything, and we proceeded like this. And we know that if these graphs together produce the complete graph, then in the end, we should still be left with only one vertex. Okay, so let's write down that inequality now. So let yi be an independent set of gi according to some distribution. We don't care what distribution at the moment. Then what inequality comes out of this calculation? So let Pi maybe V is the probability that V belongs to Y. Then what's the probability that the vertex V survives? It is one to T. This is the probability that V survives. So for V to survive, each of those independent sets here should have included the vertex V, we pick these independent sets independently according to the distribution yi. So these yi's are independent across I. So you get this number. And the same calculation then tells you that the summation over all V of the product I equals 1 to T, PIV is less than or equal to 1. And we can still do the arithmetic mean, geometric mean inequality here. And what will we get? Yeah. So let me write down product over all V, product I equals 1 to T, PIV to the and we take logs, and you notice that so sorry. So I'm writing this from memory, but yeah. So if you just manipulate this and take logs, I hope you'll get this. So this is an inequality we get, and we got this inequality out of the choice of the yi's. And you see, the decision that we need to make for each graph I, they sort of take up. Sorry.
Jaikumar, don't we need m log m on the right hand side?
Sorry, yeah. Yeah, so can I just leave it as 1 over n here? Thank you. So it is 1 over n summation over all vertices of the graph log of 1 over PIV. So let's focus on this quantity. So what are we doing? We are designing a distribution for the ith graph on the independent sets of the ith graph. Now, when you design a distribution on the independent sets of the ith graph, various vertices have various probabilities of belonging to that independent set. So in other words, this is called the vertex packing polytope. So look at all the independent sets. All independent sets, you look at the characteristic vectors of various independent sets of the graph, assign some probabilities to them, and you take the convex hull. So you get a particular point here, depending on what probabilities you assign to the various independent sets. Each independent set is a characteristic vector. Yeah. Which of the vertices are in the independent set and which of the vertices are not in the independent set. You take the convex combination and you do this for the ith graph, and you get a point. And any point in the convex hull can be generated by assigning different probabilities to these independent sets. Choose that point, yeah, for which this quantity is minimum. That will give you the best inequality. Okay. So this quantity, the minimum over all choices of, yeah, so find the point in this polytope for the ith graph where this quantity is minimum, and let us call that minimum. So let me write 1 over n summation over all v log of 1 over PIV, where the minimum is over the choice of the independent set, that is the distribution of these vertices. This quantity, let me call it H tilde. So you have these graphs G1, G2, G3. Do this minimization for G1, do this minimization for G2, do this minimization for G3, and you get various quantities. You call this the entropy of GI. And what does this inequality tell us? That if the sum, if the union of these graphs is the complete graph, then this implies that so the point I'm trying to make is we had a certain proof of Hansel's lemma where we used to go around deleting things. We just generalize it and say that instead of deleting one of the parts of the bipartite graph, we could work with a general graph. And in the case of a general graph, we could retain an independent set and delete everything else. And we still had the freedom of assigning weights to the various independent set. We assign it in the way so that this quantity is as small as possible. And still we will get this inequality, I equal to 1. And let us temporarily decide to call this the entropy of the graph. Now, we got some inequality out of studying the first proof. Let us try and see if we could have done something similar for the other proof. So how did the other proof work? Remember, the other proof sort of went from this side. We first pick a vertex V at random from the range 1 to n. And then in each of the graphs where it appears, you pick an independent set which contains this vertex. Okay. So let yi be an independent set containing vertex. So you pick a vertex V, and once you pick a vertex V, you pick an independent set based on the vertex V, which contains the vertex. There are many ways of doing this. Various joint distributions of V and yi can appear. Okay. But nevertheless, no matter how you chose these yi's for the different graphs, you still get an and like last time, so there was nothing special about bipartite graphs. We could have done this sort of a computation for any graph. And so we get another inequality. And to get the best inequality, we should find that yi so that this mutual information is as small as possible. So minimize over the choice of V and yi. That is, V should be uniform in the vertex set. And then yi, V and yi should be joint random variables with some joint distribution. Yeah? V, the marginal on V should be uniform on the vertex set. And yi should take values as independent sets of the graph GI which contain the vertex. Okay. So do that minimization over this of this quantity. And let's call this H hat of G. This is another definition of entropy. And this inequality
Hi, Jaikumar. Before a very quick question on that, on the thing you're about to raise.
Oh, sorry.
No, that's okay. I can by
Yeah.
construction,
Yes.
the yi's conditioned on v are conditionally independent or no?
That's right. They
Yeah,
are conditionally independent. Once you pick a vertex B, for each of the graphs, independently choose the yi corresponding with some distribution.
But they need not be, the yi's need not have the same distribution marginals, right? They could be anything.
Yes, the graphs are different. So some
Yeah, okay,
set,
fine. Yeah.
yeah.
All right.
Yeah.
Good. Thanks. Yeah.
Yeah. So some set of vertices which are an independent set in one graph, they don't even be independent in the other.
Right.
But when you receive a vertex, among the independent sets that contain this vertex, pick one and do them independently across the various graphs. Okay.
Thank you.
And then you get this inequality.
Jaikumar, in that definition, do you want minimum or maximum?
Maximum. Yes.
Uh,
No, the minimum. Yeah, that's correct.
this is correct.
Yeah.
We want the best inequality out of this.
Yeah.
Yeah. So even if the minimum itself will
Yeah.
be greater than or equal to log n. Right?
That's right. Yeah. Minimum. Yeah.
Yeah. So the maximum would probably arise by taking yi to be the vertex v itself. Yeah. And then, yeah, then it will be, yes, that won't give us much information for every graph, probably it will be log n. So we try to, if the graph is empty, yeah, if the graph is empty, no matter which vertex you choose, you can always choose the same independent set, that is all the vertices. And in which case, you get no information. The mutual information between the vertex you have chosen and the independent set would be zero, which is what we think it should be because the graph is empty. We expect its entropy to be zero. On the other hand, if the graph was the complete graph, then when you pick a vertex, you're basically forced to pick that vertex or the set containing that vertex as your independent set. And then you have complete information, which means you have log n bits of information. So the complete graph has entropy log n, we can say. Yeah. So anyway, we have these two competing definitions for entropy of a graph. One arises out of this consideration, which was one of the proofs of Hansel's lemma. This came out of considerations which look like another proof of Hansel's lemma. Yeah. Now it turns out that actually these two quantities are equal. Okay. That needs a proof, which I won't do. Turns out that for all graphs, h tilde of G is the same as h of G. And this is a special case of Kerner's graph entropy. So, and it is a special case because Kerner's graph entropy talks about where you have a probability distribution on the vertices. Okay. So if you remember, in the definition of h tilde of Gi, I wrote 1 over m summation over v or something like that. Yeah. This 1 over m gives equal emphasis to all the vertices. You could have moved this here to P of V and then tried to do this minimization. Okay. And that would be Kerner's definition of graph entropy. In the same way, in this definition, when I said we minimize over certain pairs of random variables, the variable V will be distributed not uniformly, will be distributed according to P, and then the yi's will be coupled with those V's. Each y, the yi should always include V in it, and yi should be independent sets of the graph. Okay. And that would give us h hat GP, but it turns out that both of them are equal. Yeah. So I didn't write down what h tilde GP is, but it is this quantity. And similarly, you have h hat GP, which is the generalization of this quantity when there is a probability marginal of V is specified. You don't assume it to be uniform. And then you get these two quantities. And so you have two different definitions of graph entropy, even in the presence of a probability distribution on the vertices. And it turns out that these two quantities are the same. And both these quantities, and this is where Kerner first came up with this formula, are equal to a certain graph theoretic quantity, and that is related to the chromatic number of the product of the graph I'll explain. So you have a graph G, and you want to define its chromatic number. So you have some distribution on its vertices, and you have some edges connecting them. Now you take the nth power of this graph, that is, vertices now become sequence of vertices, and two such sequences are said to be connected if they are distinguishable. They have an edge in any coordinate. And so the independent sets in G to the power n correspond to sequences that are mutually indistinguishable. That is, they are not separated by an edge in any coordinate. And now you look at the chromatic number of this graph, but you don't look at the chromatic number of the entire graph. You would like to pick up at least an epsilon fraction of all vertices. What do I mean by epsilon fraction? According to the product distribution. Okay. And if you look at the chromatic number of this, and you take the limit of the log of the chromatic number divided by n as n goes to infinity, it turns out that it always converges, and it converges to a common quantity, and that quantity is the graph entropy. So actually we have three different definitions of graph entropy. Yeah. One is by perhaps the kind of calculations we are more used to doing in information theory, where we take repeated IID samples and then ask how many vertices if you want to pick up epsilon fraction of the vertices and manage to color them into color classes, which are independent sets, how many independent sets will you need? You take the log of that and divide it by n and take the limit as n goes to infinity. You get a number, and that number can be described. This is some sort of a single letterization. That number can be described by calculations that are performed on just a single copy, not on the nth power of the graph. And you could do calculations in two ways, either this way or this way, and they all lead to the same. Okay, good. So this is all I wanted to say about graph entropy. Let me now come back to our questions about the channel capacity. Okay. If there are any questions, I'll be happy to take them now, but you can interrupt me whenever you want. Okay, go ahead.
Yeah, please.
All right. So what is the problem? We have these n code words. And we have block length n. And we have the property that when you pick any k code words here, there is some coordinate where all q values, yes, so these are all each of these is a word with alphabet 1 to q, and whenever you pick any q of them, there is a coordinate where all q values are. Okay. And what Friedman formula show is that then n must be at least so I keep getting confused. Something like that. So there is this exponential factor times log n. So if you so if you take log m over n, you will get an inverse exponential number, and that is the Friedman formula form. Okay. Now, yeah. So how is this bound proved? Yes, given the time I have, I'm not going to motivate it much. Let me just go and tell you the proof, and then if you have questions, you can ask. Yeah. So let us pick some q-2 code words at random. Pick q-2 code words at random. From C, let us say without replacement. So what is the situation? You picked some q-2 of them. And now the property that we have says that if you add 2 more code words, then there will be a coordinate where they all differ. Right? Now, if there was a coordinate where there was collision between this code word and this code word, that is, both these code words have the same value in that coordinate, then that coordinate is not going to be interesting for us, because there is no way that coordinate will be the coordinate which gives us this property, because we need all values to be distinct, and here there is already a collision. So only those coordinates where these q-2 code words take distinct values are interesting to us. Yeah. And now if you do a calculation, if you pick these code words at random, what is the probability that this coordinate survives? What do I mean by survives? That is, two of these q-2 code words already did not exhibit a collision in that coordinate. That probability, yeah. So the probability that a coordinate survives will be exponentially small. Probability that a coordinate has no collision is exponentially small. Now, I'm not doing the exact calculation. There are some polynomial factors here, but the important thing is it's already exponential. So what does that mean? The moment you pick these q-2 code words, already most of these coordinates actually are gone. They are not going to be helpful in producing this one-to-one map that we have, that is distinct values. So that of the n coordinates, there will be only exponentially small times n coordinates where these q-2 already take different values. They take these. In this coordinate, there were some code words which took the value 1, there were other code words which took the value 2, and so on. These q-2 occupy some q-2 different classes, and there are 2 classes which are remaining. Yeah. And when you add these m minus any 2 of these m minus q plus 2, if they happen to fall across this, that is, one of the code words took this value and the other code word took this value, then this coordinate can hope to serve hope to provide this property for that set of Q code words. So I'm not writing anything. I hope it's clear. I have picked some Q minus 2 code words. Some of the coordinates get disqualified right away because of an internal collision among the Q minus 2. And when these Q minus 2, when we focus on the remaining coordinates, because those are the only ones that can provide us this witness, in those coordinates, those pairs of other code words, which we can potentially add to these Q minus 2, those coordinates will serve this pair only if this pair takes different values. So you see, what is emerging here is that every pair of these m minus q plus 2 must be separated in one of these good coordinates that survive. But the separation has the feel of a bipartite graph, which means each of these surviving coordinates product gives us a bipartite graph where t is like exponentially minus k times n, and these bipartite graphs together, they produce the complete graph on. Okay, so I hope you understand this. So what do I mean by G1 to G2? Throw away the coordinates where there is already a collision. There are t of them left. That t happens to be such a small number. Those t together should have enough ability to separate every pair out of the remaining 2 code words which we can potentially add to this set. So it must be that e to the power minus k this was our first calculation, what I call the fundamental theorem of information theory. Yeah, if you want to separate every pair here, you must need at least these many of them. This tells you that n is at least an exponential times log n. Yeah, n is at least an exponential times log n. If you did this calculation, as I have just said, what you will get, if you had kept track of the polynomials that arise, you would get k to the power 2.5 here and not k to the 1.5. Okay. So you would get k to the 2.5 here instead of k to the 1.5. And what Friedman and Komrosh observed is that, you see, there are these n minus q plus 2 code words. Some of them take the value 1 in this coordinate, some of them take the value 2 in this coordinate, 3 in this coordinate, and 2 in this coordinate. Out of these, only 2 classes survive. So the bipartite graph that arises here is not a bipartite graph where all vertices are involved, only a small fraction, a fraction corresponding to 2 out of q. Only 2 out of q contribution comes from any of these graphs on average. And if you do this calculation, you'll be able to push in a factor q in this calculation. And as a result, I don't know why I write k on this. This q to the 2.5, which I said comes out of this 9 calculation, will turn into q to the 1. Okay, so the Hansel's lemma or the use of graph entropy was only for this final step, that is the refinement to get rid of one factor of q in the denominator here, by realizing that when you take this contribution from the ith graph, only those code words are served by this graph which come from those 2 classes which are not touched by the q minus 2 code words here. Those q minus 2 have already taken away q minus 2 of these classes. Okay. So these are, the contribution is not a full bipartite graph, but a slightly skinnier bipartite graph, and that allows you to give the extra factor. Okay. So is this clear? So the argument proceeded in 2 phases. First, there was this selection of q minus 2 code words. So this was somehow I would like to call it like a density argument. You said that when you pick this 2 minus 2, already a good fraction of your columns are gone. And even the columns that remain have substantial amount of work to do, because they have to separate every pair out of n minus 2 plus 2 possibilities. And we know that that requires work. And if you use Hansel's lemma, you can say that that requires slightly more work. And that is how the Friedman-Komlose bound arises. And yeah, so there is not more to it. Yeah, you just have to, I did not do the entire calculation, but that's all. Okay. So I'm going to move on to the 4-3 channel. And if there are any questions about the Friedman-Komlose bound, the way I have described it, I'll be happy to answer.
No, I think I missed that last argument, but that's my problem. But I got the gist of it.
Yeah. So let me just say once more. You pick q minus 2 words at random. What do we know? What is the promise? The promise is that every q of them are completely separated in one of these. So we pick q minus 2 of them. If they are already not separated, that is, they collide, then those coordinates are gone. And I have asked you to sort of accept on faith that the expected number of coordinates that will survive will be like e to the power minus k times n. Most coordinates, there will be collision. Yes, when you throw sort of q minus 2 darts on this board, which has 2 parts, some dart or the other will fall on the other. Okay, they are not going to be, yeah, it's like k factorial over k to the k. K factorial is the number of ways of falling in different boxes, and k to the power k is the number of possibilities. So their ratio looks like e to the k. Yeah, and if you keep track of other numbers like square root k in the Stirling, etc., you might get k to the 2.5 somewhere, a q to the power 2.5 somewhere in the denominator. Okay, so don't worry about it. So most coordinates are gone. The remaining coordinates still have the duty of separating every potential pair of code words that we could possibly add to these q minus 2. And so you get such an inequality. In this case, the n must be exponentially larger than log.
Very good. Thank you.
All right. So now we have, so I just want to tell you about how this was studied. So again, we have the same picture, and maybe some of the confusion here will be cleared by this. So for us, Q is 4, and we want to show an upper bound on the capacity. So we want to show that if you have n code words here, and we have the property that every four of them are completely separated in some coordinate, then n must be some factor times log n. Yeah. And this factor, or the inverse of it, will be the capacity of the 4-3 channel. So the capacity of the 4-3 channel is the same question as how big this block length should be in order to accommodate a code with m code words. So we could do the same argument as before and pick 2 words at random and try to disqualify as many columns as possible. Now, here was, I think, a very clever observation of Tata. He said, if your code, so this is the code over the alphabet of size 4. So if your code is large, that is, it has high rate. There are many code words. So that means you are packing many code words in this space of 4 to the n. Then some 2 of them should be close by. Now, what does close by mean? Close by means that on many coordinates they agree. That is, we are able to produce 2 code words which agree on many coordinates. Yeah, so there are 2 code words which we are going to pick here, q minus 2, q minus 2. Yeah, q minus 2 now is 2. So we are going to pick 2 code words. And if we believe our intuition that if you have a high rate code, then some 2 code words must agree on many places. And the places where they agree are those which get disqualified for the remaining work. Okay. So let us use some existing bounds from coding theory and trade it off against the rate. So we say if your rate is high, then, or if your rate is too high, then there will be 2 code words which will agree with each other a lot. And then that means there are very few coordinates left. Coordinates where they differ. Yeah, this is what accounts for the distance. Those coordinates where they differ must be able to do the job, which means you must. So we had an inequality like this, and if you use Hansel, you might be able to put a little factor here is greater than log n minus. So we did this sort of calculation, but there were, so the moment you pick these 2 code words according to one of the bounds which coding theory gives us, there are some difficulties in carrying out the remaining part of the argument. Okay, so let me just say qualitatively that in the case of Friedman-Komlov, this random choice of q minus 2 code words did 2 things for us. It ensured that a good number of columns get deleted, and in the remaining columns, the amount of power that the ith bipartite graph had was also limited because we have picked 2 code words at random. Most probably we have picked up, we have picked up q minus 2 code words at random. Most probably we have consumed the biggest classes there. So what is left is going to be usually very tiny. Yeah? And if they are all balanced, then it would be about 2 over q of the total fraction. Okay. But if you are going to pick these 2 code words greedily, that greedily meaning you're going to open a coding theory book and find the best bound to get those 2 things, then if the code was not completely balanced, that is, symbols in each coordinate did not appear with the same frequency, yeah, then you will no longer be able to make the argument that what is remaining is a small graph. We really need, for small numbers, we care about everything. We care about how many coordinates get eliminated. We care about how much power is remaining in the remaining coordinates. Okay. And there are difficulties in implementing this naively. So Arikan managed to get some bound out of this sort of consideration. And about 5 years ago, Marco Dalai and Venkat and I, we looked at this problem again. And it turns out that instead of using the more complicated bounds in coding theory, if you use the Plotkin bound, Plotkin bound tells you how close 2 code words must be if there are many code words in your code. Then there is a way to make this all work. And what that gives you is that the capacity. So just in 2 minutes, let me explain how those, so I just need to describe to you how those 2 code words are picked. Okay, we don't pick them completely randomly. That's not how, that was what Arikan did. Arikan said, don't pick those 2 code words just randomly as you did, as Friedman and Komlov did. But be careful. in picking those two code words to ensure high collision. So here's what you do. Suppose your code has high rate. Yeah. So imagine your code words as all strings in 4 to the power n as arranged as a tree. It's a 4-array tree. Yeah. So there are 4 possibilities for the first symbol, and then there are 4 possibilities for the next symbol, and so on. Yeah. So there are 4 to the power n. And suppose your code has rate r. Then you stop at a little before r minus epsilon. So you get these subtrees here. So you have 4 to the power rn code words. Just stop a little bit earlier. So what I'm doing is not using Plotkin bound of the shell, but we go into the calculations that lead to the Plotkin bound. And the calculations, if you remember, look like this. That is, you stop a little bit before the rate at this point. That means now, how many subtrees are there? So there are 4 to the power r minus epsilon n subtrees rooted here. And you have 4 to the power n code words. That means in some subtree, there must be a significant number of code words. It cannot be that all your subtrees have only one code word, because then you would be left with only these many code words. You are assuming that your rate is high, so you have 4 to the power rn code words. So what you do is, you pick one code word at random. So now I'm giving you a replacement for the Friedman-Komlosh argument. In the Friedman-Komlosh argument, you pick the 2 code words completely independent. Here, pick the first code word at random. It falls into one of these subtrees. Inside that subtree, pick the other code word. That means among the code words which are there in that subtree, pick the other. And what does this buy us? These 2 code words already agree on all these coordinates. And furthermore, one can show that they will also agree on many other coordinates here, and they will destroy, make those bipartite graphs that arise in the Hansel argument small enough, and we will still be able to get the best results out of this process. So instead of picking up a coding theory result of the shell, we will adopt this strategy for picking the first 2 code words, and then the rest of the argument is the same as Hansel. There are technical difficulties here too, but I will not describe them now. I'll let you look up the paper and find them there. Okay. So I'm almost out of time. There was a third thing that I wanted to tell you about. So I'll need advice on what I should do now. Should I continue, or this is also a good place to start?
Go ahead. Why don't you use another 5 minutes? You think would be enough, or would you need?
So let me do what I can in another 5 minutes. And
5, 6 plus whatever. Yeah, it's fine.
I have a very naive question before we move forward, if I may. We know that Plotkin bound is good for rate 0, and you have been stressing that the rate is high here. Then why Plotkin bound and not something else? Plotkin bound is not adjusted to high rates. It's very good for low rates.
That's right. Yeah. So I mean, you can somehow use one of those other. So it's just that we were able to do this calculation for the Plotkin bound proof. Okay. Yeah. There are difficulties about. So let me just say this. There might be an overall frequency of letters in a particular coordinate. So in a particular coordinate, one of all those 4 symbols appear with a certain frequency. When you condition on a particular tree here, the frequency inside this might be different from the overall one, and that leads to some technical complications in the way the proof is done. Now, this doesn't answer your question. It turns out that those complications are somehow handleable. They can be handled in the case of the Plotkin type argument, but if you use some of those fancier bounds, they become completely unmanageable.
I can feel this, even though, of course, I don't quite understand, but yes, I can feel what you're talking about.
Yeah. So it is just that we are able to do the calculation. It would be best use the best. Yeah. It would be good to use the best bound, but we are not able to use that. Yeah. Because it is not just the distance alone that governs the calculation in the end. It is distance. Distance tells you how many coordinates go out of the game, but we don't just use that. We also use the fact that in the coordinates that survive, the adversary has been considerably weakened. The weakening of the adversary can somehow be, the amount of weakening can be calculated in the case of Plotkin-like argument. For other arguments, we are not able to do that.
Yes, I can sort of feel it, yes. Plotkin is just the averaging, so maybe there you can control what happens in the remaining coordinates, whereas in the other bounds, it's indeed not possible.
That's correct. All right, so I'll just tell you what the next result was and how it was proved in some even more superficial fashion. So we are in the q minus 1 channel. Alphabet is large, and we want to say, so large lists. So our list size is epsilon q. The epsilon is a very small constant for now. It turns out that we can push epsilon all the way to about 1/5 and still get this sort of number. So what do we want to prove? We want to prove, so we are sort of going by contradiction. You have, and if somebody has given you an n, which is much, much smaller than some exponential in q to the, it's not important what I write here, of course, for my argument now. So somebody tells us that they have a code where they have some large number of code words here, n, and the block length is much smaller, exponential q to the 1 minus 5, so some exponential times block. And what are we going to do? We will show, we want to show that there exists epsilon times these many code words, so that in no column you will see all the symbols. Once again, we want to show that if your block length was small, then it couldn't have been, this couldn't have been a good list decoding code with list size this much, because we will show that there exists these many code words, and if you restrict attention to any column in these rows, you will not see all Q symbols, which means there is a received word which is compatible with all of them for every one of those columns. Yeah. So it could be that, yeah, you got, yeah. So anyway, I'm not saying this very well. So let us say that somebody has promised us that when you take these many code words out of this, there will be a column where all symbols appear, and we are going to disprove, or we are going to argue that that should not be possible if your block length is so small. Okay, so that's the problem. So how do we do it? So what we do is very similar to Friedman-Komlosh, but we have to do it again and again. So we pick q minus 2 columns, q minus 2 rows. See, so the number of symbols you have is q, and you have picked some q minus 2 of them. Now, as it happens in coupon collector, yeah. So the q log q here is very similar to the Q log, is exactly the same as the Q log Q that arises in the coupon collector. So when you pick the first Q minus 2 of these code words, the number of different symbols you see here will not be Q minus 2. There will be massive collisions. Okay. There will be about Q over E. E is the base of the natural logarithm. Q over E symbols that do not appear at all in any of the Q minus 2 code words. Of course, there can be some stray columns here where probably these Q minus 2 were all different. Okay. But it will turn out that those columns will be very few. And what we will do is we will go and restrict our code from the original m to m to the 1 minus epsilon, where epsilon is a very small number. It's like exponentially small in Q. So restricted to these, all these columns have exactly the same symbol. So let me say that again. You pick Q minus 2. There are some columns where typical behavior is seen. In some columns, atypical behavior is seen. These Q minus 2 did not collide as much as we would have liked them to. Okay. Then in all those columns, we say, let us restrict ourselves to the those code words which have the most popular value. Okay. Most popular value. And then go to the next column, next exceptional column, restrict yourself to the most popular value, etc. Now, this will shrink your code. You will be left with very few code words. But it turns out that this number, the number of code words, the number of columns is so small that even after this shrinking, m falls more than a constant. It becomes m to the 1 minus x. Now, these columns are gone. We are left with this problem. And next time, we pick Q over E minus 2 code words from this again. And again, there is typical behavior and there is exceptional behavior where these things did produce different symbols. Again, delete them using some similar strategy, and this epsilon becomes epsilon prime. And this epsilon starts growing, but always you are left with a significant number of code words. And you can argue that if your original n was so small, then you would have picked up Q minus 2, Q over E minus 2, Q over E squared minus 2, and accumulated these many words, and still no column. The old columns have been eliminated and they are dead forever. These columns still have not produced all the symbols. They are still missing at least one. Okay. So, yeah. So first of all, I've been very vague. The second thing is this is a rather complicated argument anyway to begin with, and I was not planning to say it in detail in today's discussion, but I can understand if what I have said is completely meaningless. But I will just invite you to read the paper from 2 years ago. This is with Siddharth. And 2018. But there is a revised version. So if you send me email, I'll send you the paper. I believe that there are ideas in this paper which are combinatorial in nature, which are somewhat, they are newer than the old ideas. So those who are interested in problems such as this, I think will benefit from at least reading that paper. So I'll stop here. Thank you for your patience. I'll be happy to answer questions.
Thank you very much. And let's give Jaikumar a round of applause. Thank you very much. Are there questions?
Questions? Yeah, Arvind.
No, I just wanted to thank you.
Yes.
Gabor, did you have a question?
No, it wants to mean applause.
Ah, okay, all right. So Jaikumar,
Yeah.
thank you very much. This was a very fine talk. We enjoyed it. Thank you very much. And
Thank you. I don't know. I'm not good with tablets, so I have to do this. But
no, this was fine. I think the pace is good. So at least I was able to follow the drift of the arguments until the very end. So and that
I think that's more. Yeah. Thank you very much.
and the shortcoming is strictly local. So yeah. And thank you very much. We also thank you very much for allowing us to burgle your dinner and family time. So it's
That's fine. Thank you very much.
and thank
I
you
hope
again.
all of you stay safe, and those of you who have, and
No,
are taken
please
care
be
of by
safe.
doctors.
And let's hope we'll meet again in person soon. Yes.
Yeah.
Thank
So
you.
please do come. I mean, Arvind has been in this office, but yeah, and, Prakash has been at our institute, but he has never, I think, come up to this office. So yeah,
No,
but
no.
all of you are invited. If you pass through India, please stop by in Bombay. It's a good place. Prakash will probably confirm. The first time he came here, he said, you live in a lap of luxury. Oh, Marco is here. So yeah, Marco has been to.
Hi, Jaikumar.
Hi, Marco.
I should say that it's a wonderful part of India and a wonderful part of Mumbai where the TIFR is located, and actually Jaikumar took me around the main building there where some of the finest paintings in India are just hanging on the walls. I was just completely blown away, and of course it's a wonderful scientific environment. So I would love to come there. I'll make sure. I threaten to come there sometime soon once.
Yeah,
The air clears. When the air clears, I'll be there. Yeah.
Marco, everything is safe there in Brescia.
Yes, thank you. I hope you're safe too there. But you are in the office, so I guess you're not too bad, right? Yeah.
Yeah. No, so we are allowed to. So if Bombay has opened up, in fact, our institute actually asks everybody to show up. Yeah.
Ah, okay, that's good.
People living far away are given some sort of concession. They are allowed not to come, but officially everybody is invited.
Oh, I see. That's good. Yeah, actually, I would like to come there too. It was very nice to visit you.
If you were in TIFR, you wouldn't want to go anywhere else. It's a lovely place.
And the temples, I remember the temples that you showed me.
Yeah. Yeah. All right.
Thank you very much. Bye. Stay safe. Thank you.
Yeah.
Hi.
Thanks.
Thank you.
Bye.
Thank you.
Bye. Bye.